Welcome back, everybody, and welcome to the lectures of February the 5th. So just a quick overview of the plans for this week. So the main emphasis this week is to look at neural networks with codes and physics-informed neural networks. Essentially what this means is that we are going to use neural networks to solve differential equations, ordinary ones, and partial differential equations. And if we get time, we will start with convolution neural networks. If not, that will be the main topic which we will start with next week. Then during the lab sessions, there will be discussions of different project paths. So as usual, this Jupyter notebook which you're viewing now is something which you can access from the standard link which we have, this pub and week 3, and then you go to the Jupyter notebook. Now, just a quick reminder of some literature which can be relevant. One is about the mathematics of deep learning, and there are 2 textbooks which are freely available. One is a longer one, of some 500, 600 pages, and then there's one of 100 pages here, which also gives a pretty good insight into the mathematics of deep learning. And then we have the textbooks which we are using during the lectures. So Sebastian Raschka's book and co-authors is one which contains many nice PyTorch examples, links well with scikit, etc. There's a textbook by David Foster, which also contains many examples in TensorFlow. So using these 2 textbooks give you a lot of examples in these different programming languages. And for many of the theoretical topics, both with for discriminative methods and for generative methods, we are going to use Goodfellows and Benjo's and Cowill's text. But when we come to generative methods, we are going to also add lots of own notes, which will complement what these people actually have presented in their textbook. Now, for this week, since we are in the stage where we are looking at neural networks and the implementations of them, then the chapters 11, 13 of Raschka. And if we get time and go into CNNs as well today, although most likely this will be the topic for next week. And for CNNs, chapter 9 of Goodfellow gives a pretty good description of it. We will also focus a lot on the mathematics of CNNs. There are also some excellent videos, which I normally recommend to take a look at. There are most likely many other ones. So feel free to use the one which you like the best. So if we now just look at what we did last week as a very quick reminder of what is coming today. So as a quick reminder, the architecture of the network is what defines our model. And this model is then defined by, obviously, the input and the output layer, which defines our data. And the output layer produces the output, which we normally label with a white tilde. Oh, there is a typo here. Sorry for that. I will correct that one. And then this is compared through the cost/loss function or error function. It's then compared with a target value y, which are the data we want to reproduce. And then the model itself, or the parameters which we need to optimize, are then given and defined properly by the number of hidden layers and the number of neurons. And as you remember from last time, this then translates into parameters to be optimized called weights and biases. And then this architecture contains also activation functions, and there are tons of those. We listed many of them last week. And these activation functions then also make up the architecture of the network. However, the activation functions are not trained when we do the optimization. So what we train in the optimization are the weights and the biases of the network, which are then defined by the number of layers and the number of neurons or nodes or units, as we call them, for each layer. So that means that you would run the calculation, the optimization part, with a fixed activation function. And it's pretty normal to have the same activation functions for all the hidden layers. And then obviously the last layer, the output, may have different activation functions. And these activation functions, they just reflect the type of data which you want to reproduce. So as we mentioned last time, if you're dealing with a classification problem, and you want to test your code on the classical MNIST data, which consists of roughly 60,000 handwritten numbers, and the code examples are those which you find in the lecture notes from last week, then you would typically have 10 output nodes, and you would use an activation function, which is called a softmax. Then, if you are dealing with a typical regression problem, where you want to produce one output value, then typically the output layer does not have any other activation function than just spitting out the value from the last node. And finally, you need to define a cost function or loss function, which is used to gauge the quality of the model. Then when you have set up the architecture of the network, then you have the optimization problem itself. And if we are dealing with a typical mean squared error, and the case here is a case which reflects a standard linear regression, where you have a linear behavior in the unknown parameters data multiplied with the so-called design matrix, which then contains your input data defined by the features and the number of input variables which you have. This is the example which you would typically encounter when you set up the mean squared error to be optimized using linear regression, because you have a linear dependence on the unknown parameter data. When we are dealing with a neural network, you would replace this x times theta here, which are either matrices or vectors. You would replace that with a neural network. And this function represents one of the many possible ways you could define the so-called cost function. And as I say here, just note that this assumes a linear dependence on the unknown parameters data. And this is generally never the case, or very seldom the case. And the parameters of the network are typically the weights for each layer and for each node. And they link to the nodes between two different layers. And then we have every node is also linked up with a bias, which becomes one another parameter here. The other ingredients which you encounter when you set up a neural network is obviously ingredients which link with the optimization problem. And many of these are just based on so-called quasi-Newton methods, or approximation to the standard Newton methods for finding the roots of a function. And the plane gradient descent, where you typically have a constant learning rate, you have a gradient descent with momentum, you have then adaptive gradients, root mean square propagation, adaptive gradient with momentum, Adam, and many other. And then obviously stochastic gradient descent is the standard approach. So these notes here are just meant to remind you of some of the basic properties which we have encountered with neural networks. In addition, you will also have typically hyperparameters which are linked with a type of norm which you choose, whether you have a norm 2, norm 1, or other types of norms. And what we are going to look at is now it's going to look at the solution of differential equations. And in particular, what we're going to focus on is first the standard diffusion equation, which many of you probably have encountered. And we are going to look at how to solve that in one dimension. And then we are going to modify that one to the diffusion equation with a stochastic term, which then is called the Black-Scholes equation. And it's a famous equation in finance, which led to the Nobel Prize in economy to Black and Scholes. And this obviously gives us the kind of machinery which we're going to develop gives us many other possibilities. So this forms one of the possible project paths, and I know that many of you are interested in solving differential equations. So the examples which you will find in the notebook here, which we had last week as well, and which we gave you as a kind of quick assignment to take a look at. This is a notebook which we are going to look into now. But before we do that, let's try to motivate the introduction of what we call physics-informed neural networks, and how that differs from what many of you have seen previously. So for those of you who followed a earlier course on machine learning, like Physics SDK 3155/4155, there we solve differential equations by simply assuming a guess for the neural network and its links with boundary and initial conditions. And then we chose some very simple ways by which we would parameterize the solution. So let's quickly remind ourselves of that before we jump into the Jupyter Notebook, which details the basic mathematics of physics-informed neural networks. And the hope is that by looking at these examples, you can tailor these notes to other types of differential equations. So if you're interested in solving the Navier-Stokes equations, that's another possibility. If you want to look at, let's say, the wave equation or other differential equations, it doesn't need to be a partial differential equations. It can be an ordinary differential equation, like the equation for the pendulum, and where you may actually look at the chaotic motion and see how your neural network behaves when you're solving a differential equation with chaotic motion. It could be the Lorentz attractor, etc., etc. So the type of differential equations is something which we will, in a certain sense, leave to you. And the examples which you will see in the lecture notes can then serve as just as a kind of guideline. Now, you should also feel free to change what we propose, because if you go to the project part, you will find a file which is called the pins, either as a PDF or as a Jupyter Notebook. And that describes a possible path. But you could also, when you have a differential equation solver, you could use that as a training point and use it as a feed into a recurrent neural network, which we are going to discuss a little bit later. So you could solve your differential equation for some few time steps, and you would use the results at every time step as an input to a recurrent neural network. And then the recurrent neural network, when you have trained it, can then be used to make predictions. But now, what we're going to do is to simply switch over to the whiteboard and remind ourselves a little bit of what we, of a simpler approach, which we can start with when we want to solve differential equations with neural networks. So let's just switch to the whiteboard. So when we are going to solve differential equations, if we now take a very, very simple case, and we are going to look at the basic way by which we could set up things. So let's take a pretty simple differential equation, and let's now say that we have a d of x, and this can be time, a time-dependent function. And then we could simply say that this function here is something which is now given by some parameter, lambda times x of t. Then it's pretty common to have some initial conditions. So in the initial conditions, what we would have then is to define some x at t0. And we could define that one to just be labeled as x with a subscript 0. Now, when we are solving differential equations, it's pretty common to discretize the problem. So as a quick reminder, we're just going to look at how you could solve this in the simplest possible way, which is actually Newton's method. So the typical approach which we will do is to discretize the variable x and discretize the variable t. So that means that our t goes now over to a variable with a subscript I. So this is a discretized time. And this is given by some t0 initial time plus some variable I, which is now the step we are making and placing us at a given time step. And then this is multiplied with the size of the step itself, a delta t. And typically this I is defined from 0 to 1, 2, and up to a final point n. So this is our discretized value for time, if we want to use time for t. And then in a similar fashion, our x of t translates into an x of t of I, which we often simply just write as an x with a subscript of I. Now, the standard ordinary differential equation solver is often based by us approximating the derivative. That means the left-hand side of the equation. So one of the standard approximations for the derivatives, if we now use a Taylor expansion, is what leads to Euler's formula. But let's now just set up the Taylor expansion and the way the expression is going to look like. So if I now look at my dx of t of dt, which we simply write as a d of x of dt, if we now Taylor expand this one, that means that we have a function x, which is now expanded around a point. So we would typically say that we have an x, which is now given by a t of I plus minus some delta t. And if we Taylor expand this one, we will obviously have a value at the t of I. And then we have the first derivative, which now has plus minus delta t. And then we have obviously the first derivative of d of x of d of t at t equal to t of I. So I hope you don't get offended if I remind you of a Taylor expansion. And then we have the higher derivatives. And for the second derivative, the plus minus just becomes a plus. So we have 1/2 factorial, and then we have delta t squared. And then we have the second derivative, dt, and this is evaluated again at t equal to ti. And then we have higher order terms, which we just simply write as a delta t cubed. Now, if we now just truncate this equation at the level of the first derivative, and then we focus only on the step where we move one step ahead, that means t of I plus delta t, then we can approximate everything with what is normally called Euler's method or Euler's formula. So what we get then is that we have the derivative d of x of d of t. So in principle, this is going to be given by x of t of I plus delta t minus x t of I. And this is divided by delta t. So if we don't do any truncations, this contains higher order terms in delta t, which now go like delta t to the power of 1. So we simply just divide by delta t here, and then we just reshuffle a little bit. So if we now skip the high order terms, this means simply that this dx dt can be approximated with x, which we now rewrite as an I plus 1, so one step ahead, minus x of I divided by delta t. And this gives us then the recipe for integrating up, so which simply tells us that we have x of I plus 1 is now equal to x of I plus delta t of dx dt. Now, in our equation, we now have an analytical expression for the derivative. And that means that if we go back a little bit here, we know that this derivative is simply given by the function x at the value t. So that means that in our particular case here, what we would have is a function here. We would simply replace this one with lambda times x of I. And that is now our method for the simplest possible one, which often does not conserve energy. If you're looking at energy conserving differential equations, it doesn't fare well when the step size becomes larger. But this is the simplest possible approach which we can implement. This is the standard approach. Now, if you look back at the differential equation which we had in the beginning, this equation here, when we are solving this for neural networks, we are obviously also going to discretize the number of integration points. And we can have as many integration points we want. And they would just feed in, they would be the input nodes to the neural network. But what we would typically do then when we set up a neural network, our simplest possible approach is actually to take the difference between the left-hand side. So we just define a new function, which I'm going to call for a function g of x, which is going to be the difference between the left-hand side and the right-hand side. So minus lambda of x, and I'm dropping the dependence on time here. And this is obviously a function which we want to drive to 0. If we have the exact solution, this should be equal to 0. Now, this function here allows us now to actually make an ansatz for the solution X using a neural network. So what we could do then, and this is typically what is done, is that we could now define a cost function which is simply given by this function g of x squared. So that means the difference between the left-hand side and the right-hand side. So this is one of the simplest possible ways we can get started with looking at the solution of differential equations with neural networks. So we could now define a cost function, which is simply this function g of x squared, and then we do that for all the possible values x of I which we are setting up. So that means that we could now define a cost function which will depend on the variables x, and which would now simply be the sum over all the i's which we have from 0 up to n minus 1. And then we would have a d of x dt. And then I'm going to write this one as evaluated, that t equal t of I minus lambda. And lambda is now multiplied with x of I. And then we square the quantity. Now, what we are going to do then is to make an ansatz, or we need to have a starting guess for the x's. So we set up this difference between the left-hand side and the right-hand side, and obviously we want to drive this difference to 0. That is the value which we are searching. Now, when you now look at this equation here, we are going to make an ansatz, and the simplest possible way is to now make an ansatz of this x of I, which is now given by some function, which I'm just going to call h1 of t of I, and plus a new function, which I'm just going to call h2 of t of I, which may also contain the initial conditions. So this function here is now going to be our neural network. So I write this neural network as an NN, and it's going to be a function of t of I, but it will also be a function of all the parameters which define the network, the parameters theta. Now, the function which you see here, on the other hand, that could be a function which now contains the initial conditions. So if we now look at the function which we had here, or in the beginning, we see now that the initial condition has some value x0. So we could require that this function h1 is actually equal to x0. Now, however, if you look at the ansatz which we have here for the neural network, we have to be a little bit careful, because we would like that when this t of I is equal to 0, then the only term which survives when t of I is equal to 0, t0, then the only term which survives is this x0. So that means that what we would do then is simply to take this neural network and multiply that with t of I. So we would have an ansatz which could look like this. This is the type of approach which we would do with a neural network by a kind of minimal approach. So we would have a function now which bakes in the initial conditions. And when we have a partial differential equations, we will also have boundary conditions which also need to be baked in. Now, when we set up physics-informed neural networks, this is done in a much more elegant way. And this is what we will come back to when we move to the slides. But this will be our first simple approach to solving differentials with a neural network. So we would start with a guess. And obviously our first guess is just a neural network where the parameters theta are given random values. And then our neural network is then defined by the number of hidden layers. So we would have a feed-forward step where we then produce a new output. And then we would continue till this function here actually becomes equal to 0, or as close to 0 as we want it to be. So we would then set in something here, this h1 function, which reflects the initial conditions in this specific case. And then we know that when t of I here is equal to t0, then we know that t0 is equal to 0. We have defined that to be 0. And then we have 0 times the neural network, and then we are just simply left with x0. So that's one extremely simple way by which we can start the neural network. So the iterative process of the network then is us simply starting with a guess here, as we said, with initial guesses for the weights. We do the training with the given activation functions, with the optimization algorithm we have chosen, and then we simply drive this cost function here to 0. That means also that when we start, there is going to be a derivative of this function here, which will enter in here. And then obviously we would have x of I, which is simply given by our ansatz here. So in the beginning, since you just initialize this with random values, you can have a big difference, but then you will quickly see that this difference becomes smaller and smaller and smaller. So if you wish to look at this from a very overarching point of view, this is the essence of solving differential equations with neural networks. So one thing you should also keep in mind now is that when we last week discussed neural networks, and also in the beginning, we said that neural networks and many of these deep learning methods, they belong to the class of discriminative deep learning methods. However, there is a floating distinction here, because if you look at a neural network, the way we are using it now, we are using that to generate a solution. So in this sense, a neural network, the way we are employing it here, is something which you would simply say, hey, this is actually a generative network or generative method because we generate the solution, starting with a guess. So what we're going to do now for basically the rest of this lecture, we are going to dive into the Jupyter Notebook, and we are going to look at how we can start solving differential equations. So the change here, if you look at this specific equation, which we have set up here, if you then have a partial differential equation, you will also have something which will depend not only on time, but it will also depend on some spatial variable, which then dictates what the boundary conditions looks like. So you could then, if you want to keep this brute force approach, you could then bake into this ansatz here, something which reflects the boundary conditions. But this is what we will bake in when we now are setting up the physics-informed neural networks. So let's now dive into the Jupyter Notebook, and this will keep us busy for quite some time here. So we are going to switch to this notes on the Black-Scholes equation. So if we do that, let's just get started here. So the type of machine learning methods, which are called physics-informed neural networks, that actually represents a novel approach to solving partial differential equations. And I have, through the last years, I've been actually solving complicated quantum mechanical problems using neural networks and also physics-informed neural networks. And with some very simple inputs about the physics of the system, they are capable, as a universal approximator, to get an amazing accuracy for the solutions. And in those cases where you have analytical solutions to compare with, which is the case you will see now when we're going to look at the diffusion equation in one dimension, you will see that we get an error. That means a difference between the analytical result and the numerical result with a pretty shallow neural network, which runs at the order of 10 to the minus 5 or even 10 to the minus 6. And that is amazing because one of the big differences between using neural networks and standard partial differential equation solvers, either using finite difference methods or finite element, finite volume elements, is that you often have to change method when you move from one equation to another one. It means also that you may have to change method even when you move from one dimension to two dimensions. If you look at the diffusion equation, you would have implicit methods like the Crank-Nicholson scheme for the one-dimensional case. But when you go to the two-dimensional one, you may opt for iterative methods for solving the equations. And that means that every dimensionality requires some changes. A neural network is in principle agnostic to the type of differential equation and the dimensionality we are using to solve the equations in. So what we are going to show here is that the pins do not require the typical discretization which we have for solving the partial differential equations. And for those of you who come from a field like finite element theory or finite volume methods, finite difference, you will now see really the benefits of setting up a differential equation solver with a neural network. And they are extremely flexible. And what you will find here is actually an application to first a diffusion equation, and then there is a deep discussion of the Black-Scholes equation from finance. Now, if you don't want to study these type of equations and you want to replace them with other ones, we hope that these slides can guide you in your own definition of the project. And these codes were actually developed by 3 former students of this course, and we are basically using PyTorch. I tend to use PyTorch more and more instead of TensorFlow and Keras. What you would need then is simply to have installed PyTorch, NumPy, Matplotlib, which are standard libraries, which basically everybody has. And then it can sometimes be also convenient to have scikit-learn as a library. So the diffusion equation, just to quickly remind you of that one, this is the 1 plus 1 dimensional equation when we are staying with one spatial dimension. So we have a function which depends on x and t. This is normally called the kinetic energy term. And this would then be the term which is only dependent on time here. And it's a first order differential equation in time and a second order differential equation in the spatial degrees of freedom. And the diffusion equation is, many of you may have encountered it as the heat equation. You have many other types of applications of the diffusion equation. So for us, the type of application is less interesting. We are just going to look at the basic mathematics here. The constant d is called a diffusion constant. T is time here, and x is a spatial coordinate. So when you look at this equation here, we need now, since you have 2 variables, in order to be able to solve it, we need to define initial conditions. And one initial condition could now be something like this. And the example here could be you having a rod of a given length, 0 to L. And you could think of, if you're looking at this as the distribution of heat along a one-dimensional rod, you could then think that at an initial time, t equals 0, then the distribution of heat, these equations, the way you see them, they are dimensionless. So we've taken away all dimension in the different constants. You could think of that as a sign distribution. So if you think of your rod, you could have a less temperature at the ends, and then inside the rod, the temperature could be higher. Then if you place this rod into, let's say, water, a lake, then after some time, the system reaches the most steady state, the equilibrium situation. And in the equilibrium situation, what you have then is that this distribution here of heat is simply going to become uniform over the whole rod. And that means that this sign pi times x here, that develops slowly and slowly towards just 0. So that means that there's a uniform heat distribution in the rod. And then we have boundary conditions. So we require simply that the values are 0 at the 2 endpoints. So these are the simplest possible Dirichlet boundary conditions, which many of you have encountered when you've taken a course in solving numerical differential equations, either numerically or analytically. So we need to import the different packages. So when we look at the pins here, we are going to import the optimization part. We are going to import the NN part, which is the neural network part. And then we just import torque share. So when we've done that, we can start defining the pin class. So this is a physics-informed neural network module for solving the diffusion equation. So we need to initialize the model. We have a parameters, which then defines the number of features, the number of hidden layers. This is the inputs. We then have the number of neurons in each hidden layer. And then we also need to define a device on which to perform computations. So here we define the different parameters. And then we can also specify how many layers we want to. So the layers are simply just given by the number of inputs and the number of neurons here. And then we have a specific activation function, which we can define. And then we simply have a loop over the range of the number of layers. And that sets up simply the number of layers. And typically we keep the same activation function for all the hidden layers. And then we define the output layer. In this specific case, I want you to mark that we are just spitting out one variable, the value of the function, and we are not using an activation function. So we normally often call this as the linear output. And you see that reflected in here. Then we set up the model here, which is a sequential, set up by the number of layers, and then we are setting up the device we want to. And then we simply set up the different initializations. And then we use the so-called Xavier and Gloraux normalization or Gloraux-Benjot initializations. And then we initialize all the parameters to 0 here. And then we have the feed-forward part. So this is essentially us setting up the feed-forward pass of the model. And this then returns just the model here. Then we need to define the loss function or the cost function. And this is the interesting part now in the setup. So previously what we said when we looked at this simple example, so suppose now we have a given number of points for which we want to make the fit here, then you see now that here we are setting up the difference between the right-hand side and the left-hand side of the differential equation. So this essentially is just us looking at the discretized version of the left-hand side and the right-hand side. And if we go back to the differential equation, what we are simply doing now is we're taking the difference between these two sides. So this defines one part of the cost function. And then we need to set up the initial conditions. Now, in our case now, instead of having a specific value, we would now set in the initial function here. And then we would then have a sine function. So that means that the optimization now, if you think back to the previous case, which we had for the simple differential equation, this was much more fixed in the sense that we put the initial condition equal to x0, and that wouldn't change. But now in the optimization itself, we optimize both the cost function as a difference between the left-hand side and the right-hand side, but we also take the difference here between the initial conditions and the value of the function, which we typically start with as a guess. And then we also have the boundary conditions. So that means that we have the left boundary condition and we have the right boundary condition. So in our specific case, the boundary condition is, if we look back at the equation here, the boundary condition is simply set to 0. So that means that we are just now squaring the value of the function as here. So in principle, in here, you should have had a -0, but there's no point in setting up that one. So this would be the left boundary conditions, and then we have the right boundary condition. And that means that the total loss function is now simply defined as the difference between the left-hand side, the initial conditions, the left boundary conditions, and the right boundary conditions. And these are the quantities which we're going to optimize. So the difference between that extremely simplistic approach, which we put up in the previous case on the whiteboard, is now replaced by a cost function which is physically motivated or motivated by the boundary conditions and initial conditions. So the training objective is now to minimize this function here, prompting the network to learn an approximation to the PDE solution that adheres to the given initial and boundary conditions. And that's the basics of a PINS approach. So then to enforce a diffusion equation as a constraint in the neural network, we simply need to compute the temporal and spatial derivatives of the network outputs. And then this is where automatic differentiation comes in. And that means that we are using autograd, which then enables the computations of these derivatives efficiently. So if you're using autograd, you're neural network implementation of a differential equation solver becomes almost agnostic to the kind of case you want to look at. So what you would need to specify is obviously the differential equation, which reflects your science, and obviously the boundary conditions, which then reflects either the physics or the chemistry or the geoscience or the bioscience of the system. So we should now take a quick small break, and then we are going to look at the PDE solver, and then we are going to jump into the Black-Scholes equations right after the demonstrations of how we can solve the diffusion equation by using neural networks. So what we are going to do now is to first look at the loss term, which needs, the first loss term, which actually needs the derivatives. And what we have then is the need to calculate the residual diffusion equation, which then enters the loss function. So let's quickly repeat the expression which we would need to have the derivatives of, and that is actually this expression which you see here. So let's now just go back to this code, which is just called def PDE, and we need the input tensor containing spatial and temporal coordinates, and the first column then represents the spatial coordinates, and the second column the time coordinates. And then the neural network which is used for the prediction is simply given by this torch neural network module here. And then we set up the residual of the diffusion equation. So we have the need to set up the spatial coordinates and the time coordinates, and we are setting up the gradients, the variables in time and space. And then we simply predict a function where we now have a specific value for the function on the model. And we compute the first derivative with respect to x. Then we compute the second derivative with respect to x. And finally, we have the time derivative. And with that, we return just the difference. And this is a quantity which we square. So when we then need to look at the initial conditions, we need to set up a corresponding function for the initial conditions and the boundary conditions as well. So if you remember back, for those of you who followed Physics SDK 3155, 4155, then we used this kind of hard constraints, which were just hard-coded. If you look back also at the notes which we had on the whiteboard before the break, there you will see that we had actually hard-coded the initial conditions. But now we have much more flexibility in the way we are setting up the initial conditions. So this just returns the model here minus the model, the value at the time equals 0, and then it simply takes the difference between this quantity and the initial condition, which is given by this sign function. Then we have the boundary condition left and the boundary condition right. So we have a u left where we plug in the values, and then we have the right one where we plug in the values for the right. So now we have all the ingredients which are needed in the cost/loss function. Then we have the training step. So before we compute the final loss or slash or cost functions, then we need to back propagating and updating the parameters. So before we do that, we reset the gradients accumulated in the optimizer by calling optimizer 0 grad. This is a standard step in training neural networks with PyTorch, as gradients are accumulated by default. So just keep that in mind when you're using PyTorch. Then we have the training step. So we now perform a plain, simple training step. So we have the input tensor containing the spatial and time coordinates. We have the one which contains the spatial and time coordinates here, the x right and x left. We have the input tensor containing spatial and time coordinates, so the collocation points, so the left and right boundary. And similarly for the initial conditions, then we need to define the optimizer, and then the neural network model, which is used for predictions. And then it returns a torch tensor. It returns the cost function for the partial differential equation, for the initial condition, and for the boundary conditions. And then it has also the function for the right boundary conditions, and then also the total loss. And this is essentially what it is doing here. So we reset gradients, we set up the different contributions to the cost function. So we have the total function here, and then we back propagate. We have the optimizer step, where we update the weights. And this simply returns these different functions at the end. So we have the analytical solution, which is set up here. And when you're running this, you can also define whether you want to run on CPUs or GPUs. So my laptop doesn't have GPUs on it, so this is just running on CPUs. But this is something which we strongly recommend in this course, is that you get an account at the University of Oslo machine learning nodes. So you just simply search for ML nodes UIO. And then as a registered user at the university, you should have access to these machines. And there you will have access to GPU units which you can run. So you can then specify if you have GPUs, else you would just use a CPU. So in my case, you can see here, it just prints a CPU. This is a pretty simple test you can run on your laptop if you're not sure of what you have. Then we are setting up the number of training points. So this is 20 points. It's just a set to 20. And we are making the comparison with the analytical result. We set up the X-base and the time data from 0 to 1 in both cases. We are setting up all the different arrays which are needed for setting up gradients, etc. Define the initial condition coordinates, and we reshape the coordinates to be column vectors, and then we combine the spatial and temporal coordinates. We convert the coordinates to tensors on the chosen device, and then we define the left and right boundary coordinates. When we've done that, we are ready. We can initialize the model and do the training. So we initialize the physics-informed neural network and set up the parameters. It has 4 hidden layers in this specific case. It has 32 nodes in each, and it uses the Adam optimizer. And in this particular case, we're just running with 1 learning rate. So when you're setting up your own code, what you would do then is to set up a array of learning rates, but you would also add hyperparameters, which could be of the norm 2 or norm 1 type. So the code here does not implement a U running over a grid of learning rates. So this is just a fixed learning rate. So ideally, you would then have to try to optimize that. So initialize the model, which is set up here. You can now see the number of inputs, number of layers, number of neurons, etc. And this is then, we define the optimizer, which is the Adam. And then we have the learning rate scheduler, and we also have an exponential decay for the learning rate. So now ready to train the model. And in each epoch, the partial differential equation, initial and boundary condition losses are computed, combined, and used to update the model parameters. And then the learning rate here is actually reduced every 100 epochs. So we start with actually this number of epochs is something you can play around with. And depending on how much time you want to spend on the problem, it sets up the, for each epoch, it sets up the different loss functions. And it prints out in units of 100 epochs, the results. And here it simply writes out the loss which you have. And you see it's actually pretty good in the beginning, 10 to the minus 3. And then you also have the losses or the cost functions for the initial conditions and the boundary conditions left and boundary conditions right. And you see that we are actually already in the beginning here, it doesn't look that bad. And if you then scroll down and you run through your 7,000 epochs and print out every 100 one, then at the end, you have roughly an error of between 10 to the minus 5 to 10 to the minus 6. Some small spikes here and there. So this is a function number of epochs. But then this is also a model where we just have trained with a 20 times 20 grid for training. And when we now want to evaluate the model here, we can now plot the results and compare with the analytical result, which you also have for this specific case. So when you're plotting, you need to work with either NumPy arrays or standard data structures like list. So PyTorch, this is one thing you have to think a little bit about, and not directly compatible with matplotlib's functions. So it's convenient sometimes to convert a tensor to a NumPy array. So the tensors, which are the PyTorch tensors, which are used in model training, are typically part of a computational graph, which is necessary for gradient computation during backpropagation. However, for plotting, gradient computation is relevant, and then there is a detach which removes a tensor from the computational graph. So that means that the unnecessary computational resources are not used. So if your PyTorch model is running on a GPU, the tensors containing the model's outputs will also be on the GPU. And matplotlib, however, does not support plotting directly from GPU tensors. So the CPU method ensures that the data is transferred back to the CPU, where matplotlib can access it. And what you have at the end here is just a plotting of the results. So we have analytical solutions, and you can see typically the predictions here, where you have an absolute root mean squared error of 10 to the minus 4. And you can see now that the solution is actually having quite small errors here. So if you now look at the further paths of the diffusion equation, so what you could do then, after this simple demonstration, is, so let me see this, here we are. No, not here. I actually went a little bit too fast here. So one thing you could do, if you want to solve quantum mechanical problems, is to realize that the diffusion equation is actually nothing but the Schrödinger equation for quantum mechanics, but in complex time. So if you take the standard diffusion equation, which looks like this, and then you perform a imaginary time rotation, it's normally called a Wick rotation. So if you, there's a formal similarity here. So if you let time go over to imaginary time divided by the h bar constant, Heisenberg's constant, then, and you replace this density here, resolution, with a wave function psi, and you replace this parameter d with h bar divided by 2m, then you can actually rewrite the equation as a diffusion, as a Schrödinger equation. So you see then immediately that you would have d times the second derivative here, which simply becomes equal to h bar divided by 2m times the second derivative of the wave function, and then you have minus I divided by h, and then the first derivative. And then you actually have Schrödinger's equation. So if you apply the substitution, what you get then is essentially the diffusion equation in imaginary time. And that's what you see here is a free particle Schrödinger equation. So this could be, if you also add an external potential to it, it could be an approach where you now try to solve the quantum mechanical problem using physics-informed neural networks. And this is a very hot topic, and research shows that you are actually getting a pretty good, with pins, a pretty good reproduction of both analytical results and also other results from other numerical methods, often with even better accuracy. Because when you're solving these equations here, you have a benchmark on the Schrödinger equation. If you have the exact wave function, the solution to this differential equation, then the variance of the expectation value of the energy is exactly equal to 0. Now, what we are going to look at is, however, a slightly different problem here in the exercises and the lectures today. And this is about the so-called Black-Scholes equations. And in principle, this is a diffusion equation with a stochastic term. And in the notes which you find here, you will see how you can solve this equation here using physics-informed neural networks. So that means that in addition to the fundamentals implemented and discussed regarding the diffusion equation, you can add more functionality and experiments to show how a possible project on pins may look like. And this file is written mostly, which you see here, to be pedagogical, and this contains phrases and formulations not necessarily suitable for the more formal project that you would write. So when you look at everything which you see here, when you write the final project, many of the things here are not needed to plug into the project. So hopefully the way we just described the system and the solution of the equation is something which you can find useful. You could, if you want to, look at the solution of the Black-Scholes equation as part of the projects. That's one possibility. Or alternatively, just look at this as an interesting example. So in finance, if you're not too familiar with the Black-Scholes equation, an option is actually a contract which gives the owner the right to buy an underlying asset at a set time in the future, which is called the time of maturity. And then the underlying asset can be everything from stocks to currencies to some commodities like oil or other types of commodities. And in a way, it's a kind of, if you want to simplify it, you could say this is just a form of betting. So actually pricing options is a major challenge in mathematical finance. And there are several algorithms which have been used to address this problem as far back as the early 80s. And these approaches, although these approaches have become more advanced, the complexity of the financial markets still makes options difficult to model accurately. And advancement in machine learning have established neural networks as a powerful tool for this, due to their ability to handle large data sets and capture complex patterns. So in the last years, there's a lot of research in what you might call financial engineering. It's a field by itself, which has been dominated by stochastic processes, Monte Carlo methods. And in the last years, what people have seen is an extended usage of neural networks to model financial markets. So one model which has been extremely popular is the one after Black and Scholes. And this is a model which aims to estimate a fair price of an option based on certain assumptions and market conditions. A fair price means simply a reasonable price, considering the price of the underlying asset and when the option must be exercised. In this model, the price of the option, which is normally labeled with a C and a variable S and T, where S is the underlying asset and T is time, is governed by a partial differential equation, which is the Black-Scholes equation, which is a diffusion equation with a complex term. And we are going to see that pretty soon now. So in addition to the constraints which are provided by the equation, you can then train a pin network on real-world data. One of the problems here is that if you want real data, unfortunately, you often have to pay for it. But there are simpler data sets which we can set up if you want to use this as a framework for project number one, or even for a full semester project. And then when we look at this problem here, so you can train a pin network on real world data as well as the underlying differential equation dictating the distribution of the data. And since the price of an option in the Black-Scholes model is governed by a partial differential equation, it is actually natural to ask the question of whether physics-informed neural networks can price options. And this is what has motivated the construction of a pin model that solves the Black-Scholes equation. And when you go down in the slides here, you will also see that there is an extension to a multi-dimensional Black-Scholes equation, which is actually a generalization of the Black-Scholes equation, such that the option can have multiple underlying assets. This is normally something you can think of as an option on a portfolio of assets. So let us now take a closer look at the Black-Scholes equation itself and just quickly remind ourselves about the heat equation. Now, if you look at the Jupyter notebook and what comes after the basic introduction to the Black-Scholes equations, there are lots of numerical experiments in the Jupyter notebook itself. And we will not cover all of them, but we invite you to take a look at many of the runs which you will find below here, because they can be instructive for the implementation of your own physics-informed neural network. So we will not cover everything in the slides here, and you will see that in the end here, there is also a set of experimentations with the depths of the network, type of activation functions, type of optimizers, etc. These will be part of your numerical experimenting with neural networks. So the differential equation which we are going to solve is a lookalike of the diffusion equation. And the basic equation, if you now start with the heat equation, and you have a constant sigma squared, where you previously had the diffusion equation, there's a short change of variables here, which we need to introduce. So the x's are now defined in terms of the ln of s divided by k, where s is this underlying asset price, and k is the so-called strike price. I mean, the definitions of these quantities are given in the text here. And the tau is then defined in terms of, this introduces a new time here, and which is defined here, as you can see. So these are scale quantities. And this is something you would always do, is to scale the equations. And u is given by a function which depends on this quantity c, which we are coming back to, of what it is. So, but the s and t are the underlying asset price, and t is now the current time. And this alpha and beta are parameters to be chosen. And x is now changed into the log of the asset price divided by what's called a strike price. So I don't have the in-depth knowledge of this kind of financial quantities. And these are things which we have just taken from standard textbooks in financial engineering. So when you do this change of variables, you have the derivatives, which are then relevant for solving the equations, which are simply obtained by the chain rule. So if you then replace the variables in the differential equation, which is this one, which is a lookalike of the standard diffusion equation with these new variables, then you end up having to compute these different derivatives here. Then you substitute these into the heat equation. When you plug these into the heat equation, then what you get is a set of equations which you can rearrange, which then ends up with this equation here. Then choosing these parameters alpha and beta, you can pick them so that the term C and C of S combine into the so-called Black-Scholes term. And with these, you have a set of combinations here, which you then can translate into a differential equation. So that means that you end up with a final Black-Scholes equation, which has a standard diffusion part, which are the two first terms. And you can see that one, that the C is actually the price of the option. Sigma is something which is called the volatility of the underlying asset. That means how much the price fluctuates as time goes on. And R is the so-called risk-free rate. And this rate, this risk-free rate, is assumed to be a measure of how much money grows over time under the assumption of a risk-free market. So these are things which we will not say so much about. So, but if you have some background or interest in this field, we invite you to actually take a closer look at how these quantities are defined in financial engineering. And we are simply going to treat them as constants in the model here. The differential equation has also some end conditions. And this condition is at the time of maturity. That is typically when you want to realize the assets which you have. That's a set date when the option must be exercised. So typically assets time could be a month or 2 months, depending on the contract which you set up. And this defines a terminal time. And then the terminal condition is simply given by the max between S, which, just to remind you of that one, is given by the underlying asset price. K is the so-called strike price. And you would then have this condition here with the max of these quantities here. And you also notice a new term K. K is now known as a strike price, and the strike price is the predetermined price at which you can buy the underlying assets. Then there are boundary conditions. So everything here is actually a lookalike of the diffusion equation which we had, and we would simply have to implement this terminal condition. We would have the differential equation itself, which defines the basic cost function, and then we would have the so-called boundary function. So when in the limit of very large asset price, this is the kind of boundary conditions which the solution has to reach. So in the case of one underlying asset, the Black-Scholes equation has a closed form analytical solution. And that allows us to compute exact option prices without having to rely on numerical simulations or iterative methods. And something that is rarely possible in basically all real-world scenarios. So not only does this offer a fast way to price European options, but the mathematics behind the solution also lay the groundwork for more advanced models and numerical techniques, such as the multidimensional Black-Scholes equation and Monte Carlo methods, which are the more traditional ways by which you would solve the Black-Scholes equation. So if you believe, this is just an example here, that the Apple stock will increase over the next year, you might consider buying Apple stocks. And since you're not familiar with options, you will also know that you can buy an option that gives you the right to buy Apple stock at a price K in 1 year, instead of buying the stock now. And the attractiveness of the option market comes actually from the fact that the strike price K may be less than the price of the Apple stock in 1 year. So you essentially get to buy the stock at a discounted price 1 year from now. So in here, there are some specific examples which we invite you to take a look at, so you can see the difference between a stock versus the buy option and how these quantities can change over a year. So you could then find the current stock price and then the strike price, which is 22. So that means the price of option at time t equals 0 is actually equal to 2 then. And the time of expiry is t. And then you can look at the stock price at maturity, and you can look at what kind of profit or loss you would make in those cases. And this simply gives you an example of how these quantities can be understood. So you see some positive aspects of trading in options when the stock price significantly decreases over the course of a year to, let's say, 10. Buying the stock itself would actually result in losing $10, while buying the option would only result in a loss of 2. And you see also that when the stock is worth 28, which we had in this case here, at the time of maturity, buying the stock yields a gain of 8, which is 40% of the money you invested, while the option itself yields a return of 4, which is 200% of the money invested. So there's much more to why options are attractive, but hopefully this gives you a kind of understanding of the type of or the reason why the option modeling is so popular and so important. You also differ between European options, call options, American call options, etc. And these are things which we just leave you to you if you want to dive into this topic here. So what we are interested in now is simply to solve the Black-Scholes equation using physics-informed neural networks. And now, as you have basically understood what enters the equations, then for us the rest is actually to set up something which is pretty similar to what we did with neural networks. So the thing which changes, besides the differential equation itself, are the initial conditions or final conditions and the boundary conditions. So these are essentially the only thing which change, and where when you're setting up the program, you can actually take the diffusion example and then simply change the type of initial conditions, the type of equation which you have, and the boundary conditions. So if you just have one option here, the analytical equation is actually given in these expressions here. So that means that you can compare your code with the analytical expression, and that's always useful when you're developing a code, like the one-dimensional diffusion equation, which is also an equation which has analytical solutions. When you then set up these different quantities, you can then compare your code with this analytical solution here. And what we are setting up first is just the analytical solution in terms of all these parameters. And when you have set up the analytical solution, the next step is to, so this is simply the analytical solution. And here we plot the analytical solution. And then the next step is to look at, so we're not going into all these details, but we're going to just to sketch quickly how you set up your PIN model. So in the tables and print statements below, you might experience different results when running the file compared to what is printed here before. But the errors should be approximately of equal magnitude. And one thing that may happen is that the PIN performs significantly worse in one-dimensional case before the hyperparameter configuration. This has sometimes happened sometimes, but in general, you will see that you will essentially, when you run it here, you will basically get something which is pretty close to the analytical solution as well. So when you're setting up the neural network, I mean, it's essentially just a replica of what we did with the diffusion equation. So we are setting up the model with the different parameters, the number of hidden layers, the activation functions as before. So we have the same loop here, setting up the number of layers depending on how many we have defined. We loop over the layers, and we then set up all the variables which we have. And again, since we're just spitting out one variable for the output layer, so this will be the final line here, is just the output layer. And then we repeat what we did, whether we want to use GPUs or CPUs, and we have the possibility to do that. We initialize the weights, and this is defined here. And then we have the feed-forward pass, as before. And we have the training of the network, and in this type, here we need to when we initialize the data, we are normalizing, setting up the boundary conditions. This is the left boundary conditions, and then we have to set up the right boundary condition as before. So this is something which will change from type of equation to type of equation. So this is the boundary conditions. We have the PDE here, which is being set up, and as before. And we have the data sets. We generate 1D terminal condition points. We have set up the initial conditions, and then we are basically ready to run. So we have the initial or the mean squared error, which is just given by the target values minus the values which we want to reproduce. And then basically with the loss functions, and we can then simply set up the final functions for the training with backpropagation, etc. So we are not going to go into all these details. This is something which we actually, if you're interested in it, we would like you to simply take a look at the numerical experimentations, the way the terminal conditions are set up, etc., etc. So it requires you having some knowledge into this type of science, because that's the way you would be able to set up both the initial conditions, the boundary conditions, and the differential equation itself. And when you have that, the procedure which we outline with the diffusion equation is essentially the same, except that obviously the data set differs here. Now, we are going to stop here today, and we invite you to take a look at the experimentation which is done, because if you scroll down here, after all these numerical runs, you will also find the tests of different activation functions, because this is something which needs to be done. When you are exploring different architectures, one thing is the number of layers and nodes, but we also said that the type of activation function plays a given role. And it's important to explore different types of activation functions as well. And at the end of this Jupyter notebook, you will find the numerical experiments with different types of activation functions. Now, we did not get time to start with convolutional neural networks. And that means that this is something which we will spend or start with during the next lecture, and we will look at the mathematics of convolutional neural networks. So we will not continue with that today, and we will simply just stop here and leave the rest of the experimentations to you, because this is what you would end up doing anyway. But the basic message, if you now want to wrap up what we have done, is that you have a physics-informed neural network where you need to set up the differential equation you want to solve. You set up the cost or loss function, where you take the difference between the left-hand side and the right-hand side. You add to this the initial conditions. You add to this the boundary condition. But you can also have hyperparameters, which you add to these equations. We haven't discussed that here, but it's pretty common to also explore the possibilities of having hyperparameters which are accompanied by the norm 1 or norm 2, which are the most common ones. You need also to explore different learning rates. So, but that is part of the numerical experimentation, which you would always do when you have set up your basic equations. But the overarching point of view, instead of hard coding initials and boundary conditions, like we did on the whiteboard, you would now have the parts of the cost function or loss function, which reflects the boundary conditions and initial conditions. And that gives us a more compact optimization problem. And this is where we will stop today. And next week, we will begin with the basic mathematics of convolutional neural networks. And after convolutional neural networks, we are going to look at the mathematics of recurrent neural networks and how you can write your own CNN codes and RNN codes. And after that, we will continue with autoencoders, and that will be the last of the standard deep learning methods. And many of you have already encountered them, but you have probably not gone in depth into the mathematics of these methods. After that, we are going to begin with generative methods. So this ends today's lecture with an invitation to explore this Jupyter notebook in more detail. There are many more details than we will cover in the lecture here, but hopefully all the details which you find in the Jupyter notebook can be of help when if you want to solve differential equations using physics-informed neural networks. Hopefully this can be of some use.